For question 1, we want to identify the following 4 polynomials, and you could use your graphing calculator, but what I'm going to do is use the leading coefficient of each of these to match it up to the correct graph. So I'm going to go about looking at A and thinking which graph could it be. So here we have negative 12x to the 6th. A 6-degree polynomial has to either go up or down on both sides, so it can't be this or this. So it has to be either this option or this option. Since the leading number in front of it is a negative number, it means it has to go down on both sides. So for this first problem, this negative 12x to the 6th means that this is graph A. Okay, if we move on to B, here we have 6x to the 5th. So x to the 5th is odd, meaning it has to go up on one side and down on the other. Here we have 6 is a positive number, meaning it has to be this graph here. So because of this, I know that this choice is B. All right, moving along. For C, I have 10x to the 8th. 8 is even, meaning it's going to go up or down on both sides. 10 is a positive number. Can't be this graph. It has to be this one here. So again, I'm using the 10x to the 8th to determine that this is graph C. By process of elimination, I know that this last one is graph D, but if you look at the leading term, x to the 7, 7 being odd means we're going in opposite directions. A negative means it's going to be flipped upside down. Therefore, this is D. So again, I'm going to use the leading coefficient to match up the correct graphs. I'm going to start with A, and I see we have a 1x squared. So I want the graph to go, since it's a positive 1 with an even exponent, it's going to go up on both sides, and it can't be this or this. Here's the graph. So let me mark that over here. Because we have the graph of x squared, this is A. Moving on to B, negative 0.5x cubed. We're going in opposite directions, but the graph is flipped upside down. This is in opposite directions, but not in the correct order. Okay, this has to be negative 0.5x cubed. So because of that leading term, I know this is B. For graph C, it's a positive number times x to an odd value, an odd degree, meaning that it can't be this graph, but it certainly is this one. So let's see. Because of this leading term, this is graph C. And again, I can just know that this last one is D, but just making sure it makes sense. Okay, we have a negative 0.25 x to the 10th. The 10 being an even number means it's either going to go up or down on both sides. The negative number flips it upside down. So therefore, this leading term tells me that this graph is D. To sketch a graph of this polynomial without using your graphing calculator, first we need to know the degree. I'm going to put a 1 up here and note that the degree of this is going to be the sum of 2 and 1, or simply 3. The fact that it is odd degree means it's going to go up on one side and down on the other, since it will have a positive leading coefficient. Next, what are the zeros? They're the places where each factor is 0. So for example, if I put a negative 4 here, it makes this factor 0. If I put a positive 2 here, that makes this factor 0. So there are 2 zeros. One is at negative 4, the other is at positive 2. And below there, I'm going to note what the exponent on each is. For this 0, the exponent is 2, meaning it's going to stay on the same side of the graph. And for 2, the exponent on that factor is 1, meaning it should cross over. So I'm going to sketch a graph of this equation. On the x-axis, I'll count each of these as just one unit, and I'm not going to scale the y-axis. So, it's going to go up or down some amount. It's just to get an idea of what the graph looks like. So I'll plot negative 4 is one of the zeros, and positive 2 is the other. The degree is odd, meaning it's going to go down on this side and up on this side. All I have to do now is connect one end of the graph to the other. When I get to this 0, it's going to bounce off and stay on the same side because the exponent on that factor is 2. Then it's going to come up and cross through the axis and connect to this end of the graph. I expect that the equation should look something like this. Just a general sketch of the graph. You can compare this in your graphing calculator. I just typed that in. And what I did is I left the y min at, well, I did not leave it, I actually changed it to -40, and the y max I left at 10, and I changed the y scale. You don't have to do this, but I changed it to 10. And I did see a graph that resembled this, like the highlights are there, in that it goes up on one side, down the other. There are zeros here and here where it stays on the same side and crosses. For this polynomial, the degree is going to be the sum of those two exponents, which is 4, meaning it's going to go up on both sides. The zeros are the same as in the previous example since I did not change the factors, so the zeros are -4 and +2. And this time the big difference is now they both have an even degree for their exponents, meaning it's going to stay on the same side of the graph. So if I put all of this together, there is a 0 at -4. There's again 1 at 2. The fact that the degree is 4 means it's going to go up on this side and up on this side. And if I connect one end of the graph to the other, it's going to drop down. It's going to go to the 0, but the fact that the exponent is 2 means I'm going to stay on the same side. I go up some amount before I come back down and go to this 0, and then stay on the same side again. So the graph should resemble this. Now, I did check this in my calculator. I left the y min alone at -10, and I put the y max to 100. Again, just to check my work here. The y scale, I switched to 10. I thought that would be good. No right or wrong answer here for this portion, just something so you can see what the graph looks like, and that's it. So for this one, the degree is going to be 5, and the zeros are the same, again, as in the last problem. But this time, the degree for this 0 is 2, and this one is 3, meaning it's going to stay on the same side and cross. But when it crosses over the axis at this factor, the fact that it's 3 means it won't look linear. It's actually going to look like x cubed where it levels off a little bit. All right, so putting this together, what do we have? I have zeros again at -4 and 2. The degree is 5, meaning it's going to go down on this side and up on this side. So the graph has to go up here. It stays on the same side because the exponent is 2. It drops down some amount before going back up here. But this time, it levels off a little bit before moving up to this end of the graph. So this is what I'm expecting for my polynomial. All right, this one was kind of a little bit harder to see a good picture. For the y min, I went with -400, and the y max I put at +200. With a y scale, I decided to count by 100s, whatever. This gave me a pretty decent picture of this graph. For this polynomial, the degree, I'll put a 1 on that exponent. It's going to be 1 plus 2 plus 3, so it's equal to 6. I'm expecting it to go up on both sides. Now here, the zeros are -5 and 6, but also 0. If you ever have an x to a power by itself, some positive integer power, 0 makes this thing 0, so gotta be careful there. That is -5, 0, and 6 are the zeros. And I'll make note that the exponent on this one is a 2, the exponent here is a 1, and the exponent here is a 3, meaning I'm going to expect it to stay on the same side, -5, cross at 1, stay, and also cross at 6, but more like an x cubed graph. All right, so let's see. -5, 0, and 6 goes up on both sides. Okay, so the graph is going to drop down and stay on the same side. All right, it goes up some amount before going back down to this spot and crossing over. I'll kind of pause here because with respect to sketching this graph, obviously it has to come back up here, and I don't know how low this will go in relation to how high this went. So at this point, I'm sort of guessing. I'm going to say like, okay, I guess the graph drops down a little bit before going back up here, and then it levels off and crosses over. I'm expecting my graph to look like this. Noting that I really care about the ends of the graph, what happens at each 0, and then maybe I could use a graphing calculator to get a better idea of how high or low these values are. So I'm going to type this into y1. All right, after some guesswork here, I chose a y min of negative 11,000, and I put the y max to be positive 11,000. And for my y scale, I counted by thousands. And this gave me a pretty decent picture of the graph. And it did turn out that this highest point was further away than this lowest point, so my graph, I'd say, is even more accurate to the graph I see in my calculator, and that is it. All right, for the degree, I'm going to put an exponent of 1 here, and note that if I add those up, I have a degree of 4, meaning we're going to go up on both sides. The zeros are 0 and 5. For this factor, there's a degree of 3, and for this factor, there's a degree of 1, so it's crossing at both of these locations. Putting all this on my graph, I'll start with the zeros. There's a 0 at 0 and also at 5. It's going to go up on both sides. So the graph comes down, levels off a little bit, drops down, and then crosses up like this. For this one, I chose a y min of negative 100 and a y max of positive 100. I decided to count by, I guess, 50s. That doesn't really matter, but it gave me a decent picture of this graph, and it matches with what I have. All right, so for the degree on this one, each exponent is 1. Therefore, the degree is equal to 3. And my zeros are negative 1, 2, and 5 each, of course, having an exponent of 1, meaning it's going to cross over in a linear way at each spot. Filling in all this information, there's a 0 at negative 1, a positive 2, and positive 5. Odd degree means it starts down, and then it goes up. All right, if I connect this, I go up to the 0 where it crosses over by some amount, has to drop back down before coming back up, and this is my graph. I did already look at this in my calculator. I chose a y min of negative 50, y max of positive 50. I counted by tens in my y scale. That's probably like too far away, but it's still decent enough to give me this picture here. The degree of this polynomial is 5 plus 3, or 8, so it's going up on both sides, and the zeros are 0 and negative 4, both of which are odd, right? This one has an exponent of 5, this factor had an exponent of 3, so those both are going to look fairly similar. But the big difference in this problem is I have this negative value. If you multiply a y value by a negative, it's just going to flip the graph. So what we'll do is, after I plot the zeros, instead of having it go up on both sides, since the graph is going to be flipped upside down, it's going to go down on both sides. If we plot the zeros, there's 1 at negative 4, and there's 1 at 0. The fact that there's that negative means, okay, it's going down on both sides. If I connect one end of the graph to the other, I go up to negative 4. It's going to cross through after it levels off a little bit, goes up some amount, and it has to go down here before leveling off again and connecting down here. So the sketch is okay. The y min and max that I chose to compare this to my graphing calculator, I left it at negative 500 and positive 500. It was a decent enough graph. I counted by 50s, and it does match up with my answer. For this equation, every factor, if I put a 1 on there, tells me the degree is 4. And the zeros are 0, negative 4, and 3. And if I check out the exponents, the exponent on the 0 is a 1, and negative 4 is also 1, but at 3 it's a positive 2. But again, we have this difference of not only is there a negative, but there's a negative 2. So what does that do to my picture? Well, it's going to flip the graph because of the negative, and the 2 just stretches it. It's going to scale my graph after that. And since we're not really scaling the y-axis, I think the picture I get will be accurate if I just worry about flipping the graph over the axis. So again, we have this even degree, so it's actually going to go down on both sides. I'll plot my zeros. So that was 1 at negative 4, so 1 at 0, and 1 at positive 3. It's going to go down on both sides. I go to this first 0. It's going to cross over before it drops back down, crosses again, goes down some amount. I'm guessing it's probably going to be closer to the x-axis than between the two previous zeros. Goes up to the spot, but it has to stay on the same side before connecting down here. And so with the graph, the y min I chose negative 300, and the y max I just left at positive 300, counting by 50s, and that gave me a pretty decent picture. For this problem, we're going to go backwards from the previous questions, where now I'm starting at the graph and I'm using it to factor the above polynomial. So what you need to know is the zeros, and also what is happening at each of those zeros. There's a 0 at negative 1, 2, and 5. And this means that my factors must be x plus 1, x minus 2, and x minus 5. Also, the degree of this polynomial is clearly 3, which means that each exponent has to be exactly 1. And if you look at the graph, it crosses over pretty much in a linear way. You can place those exponents on here, but here's the factored form of this equation. All right, again, we want to locate the zeros. Looks like we have one at negative 4, negative 2, 1, and 3. Which means my factors must be x plus 4, x plus 2, x minus 1, and x minus 3. And since the degree of this polynomial is 4, each exponent must be 1. And that matches up with the graph, and this is the factored form of the polynomial. All right, so the zeros on this one, there are only 2, and I see the degree of the polynomial is 3. This means I'll have to be careful with my exponents, but this one is negative 3 for the first 0, and this appears to be positive 2. All right, this means my factors must be x plus 3 and x minus 2. The exponent on the x plus 3 factor must be 1 because it's going through the axis in a linear way, but this one stays on the same side. The degree is 3. To make this match up, I have to have a degree of 2, and this is the factored form of this equation. For this polynomial, we have zeros at negative 2 and 1, meaning that x plus 2 and x minus 1 are the only factors. They both must be even degree. And here, to make that match up with a 4, must mean they're both 2. And this is the factored form of this equation. All right, to divide these two polynomials, I'm going to first multiply by 2x. That gives me a 2x squared plus 2x. Now I subtract these. So 7x minus 2x is 5x. I'll bring down the 5. This means I must multiply by 5. And therefore we get 5x plus 5, which is great, meaning that when we subtract these two things, the remainder is 0. It'll probably be no surprise that the answer to this question should be x plus 1 based on the previous problem we just did. But just to make sure this works, I want to cancel 2x squared, so I have to multiply by x. So I get 2x squared plus 5x. And when I subtract these, I get 2x plus 5. Therefore, I have to multiply by 1. I get another 2x plus 5. After I take the difference, I get a remainder of 0. All right, for this one, I'm going to multiply first by 3x squared. That gives me 6x cubed minus 3x squared. When I take the difference, be careful with this minus and minus, but you have negative x squared plus 3x squared, that is 2x squared. I'll now bring down the 7x. To get a 2x squared, I need to multiply by x. That's 2x squared minus x. When I take the difference, again being careful with the minus and minus, 7 plus x is 8x minus 4. If I now multiply by a positive 4, I get 8x minus 4. The difference of these two things is 0, meaning our remainder is 0. Therefore, I factored this polynomial with these two. All right, if I want a 5x to the fourth, I need to multiply by x cubed. So I get 5x to the fourth plus 3x cubed. When I take the difference, it's negative 2 minus 3, so that's minus 5x cubed. I'll bring down the negative 3x squared. I now want to multiply by a negative x squared. So I get negative 5x cubed minus 3x squared. And when I take the difference, I actually get 0. So I have to bring down the 10x. That's, you could even say 0x squared. If this happens where you have nothing to cancel, you could put a plus 0x in this place, and then just simply have a 0 here, bring down the 10x and the 6. So we're basically just skipping over dealing with the x's because there's nothing to cancel. I'm now going to multiply by 2. And I get 10x plus 6, the difference of which is 0. For the next question, we're dividing x minus 1 into x to the fourth minus 1. If you ever have terms that are missing, it'll be useful to place those into the problem because we don't want to skip over an appropriate place value. So by that I mean, I'm going to put in 0x cubed, 0x squared, 0x, and then this minus 1 at the end. This isn't necessary. I'm placing these here so I have some spot to refer to an x cubed, x squared, and an x. Notice like in all the previous problems, the x cubes and x squareds and x's and numbers were all above each other. Anyways, if you want to cancel an x to the fourth and you have an x, we have to multiply by an x cubed. So I'm going to put x cubed here. It gives me x to the fourth minus x cubed. And when I subtract, 0x cubed plus x cubed is simply just x cubed. And I'll bring down the x squareds. I now need to multiply by an x squared. It gives me x cubed minus x squared. When I take the difference, I now get x squared, and I'll bring down the 0x. I now need to multiply by an x. I get x squared minus x. And when I take the difference, I get x minus 1. I'm at my last step. If I choose plus 1, I get x minus 1. And when I take the difference, I get 0. And that's it. All right, so I want to try one that was at least kind of difficult here where now I'm dividing by an x squared instead of just an x to the first power. Also, note that there were no x to the fifth, so I put in this 0x to the fifth to have a spot to refer to. I don't know if we'll need that, but it is there. So the question is, you want to cancel x to the sixth. What would you multiply an x squared by to get an x to the sixth? And the answer is an x to the fourth. 4 plus 2 is 6. So I'm actually going to write that above the x to the fourths. So if I place that in, I get x to the sixth plus x to the fourth. And if I take the difference, I get 0. You can put 0x to the fourth if you want, but there's nothing that's left over, and I'm going to bring down the minus x cubed. I'm thinking that I should also bring down the plus 3x squared. As we saw in the last problem, it's really irrelevant to have a 0x to the fourth. It just means you're not referring to this spot at all. So really what I'm trying to, let me put that in here, ignoring this. What I'm really trying to do is cancel this negative x cubed. I'm going to multiply this by negative x. So I'll go all the way to my x's, put a negative x here. I get negative x cubed minus x. So really, I need to bring down this negative x too. Because when I subtract these things away, I get negative x cubed plus x cubed, and you get negative x plus x, those are all gone. The only thing remaining is this 3x squared and then a plus 3 if I bring this down. Okay, so now I'm going to multiply this thing by 3. I get 3x squared plus 3. The difference of these two things is 0. So this problem was a little bit strange where the answer, what all of this means is if you take x squared plus 1 and you multiply that to x to the 4th minus x plus 3, the answer is x to the 6th plus x to the 4th minus x cubed plus 3x squared minus x plus 3. It was difficult because there was a ton of stuff that was missing that we didn't even really need, and it was like, what do I bring down? You bring down anything necessary when you're subtracting out a portion like this here. So I want to try two problems where we don't have a remainder that is 0. I think that might happen here, but let's see. X plus 2 divided into x cubed plus 7x squared plus 12x plus 10. I would have to first multiply by x squared because we get x cubed and then we get 2x squared. When we take the difference, we get 5x squared, and I'll bring down the 12x. So I now need to multiply by 5x. I get 5x squared plus 10x, and when I take the difference, I get 2x, and I'll bring down the 10. To cancel 2x, I'll multiply by 2. You get 2x plus 4, and when I take the difference here, I get 10 minus 4, which is 6, meaning there's something left over as a remainder. All this means is that x plus 2 did not divide our polynomial evenly. Said another way, if you took x plus 2 and you multiply that to x squared plus 5x plus 2, you almost get the original polynomial of x cubed plus 7x squared plus 12x plus 10. It almost worked. But you actually have to add 6 more to make this thing a true statement. So every remainder that we had before, you would basically put a plus 0 at the end, which is unnecessary. But here, it's very important because this is saying that, well, x plus 2 did not factor this expression. All right, one more here where, all right, I'm dividing 3x minus 7 into this 9x to the 4th polynomial. So to cancel a 9x to the 4th, I need a 9. So I'm going to multiply this by 3 and also x cubed. So that's my starting point. 3x cubed gives me 9x to the 4th, but also minus 21x cubed. So when I take the difference, it's really just 21 minus 12. And we're left with 9x cubed, and I'll bring down the 45x squared. So I now need to multiply by a 3x squared, which gives me 9x cubed, again, minus 21x squared. And this is really negative 45 plus 21, which is negative 24x squared, and I'll bring down the negative 98x. So now I'm going to multiply by negative 8x. That gives me negative 24x squared plus 56x. And when I take the difference, it's really negative 98 minus 56. So it's negative 154x. And I'll bring down the negative 106. So I was going to start this whole thing over because I realized I made a mistake. Oh, it is such a small mistake. But once one thing is wrong, it's not going to work out. You probably caught this already where, whoops, this was supposed to be a positive 98. I don't think we have to redo the whole problem. All I'm going to do is just put a positive 98 there. This should really be 98 minus 56. Again, I'll leave this line here, but whoops. That was really supposed to be 42x minus 106. All right, this is a little bit better because the question is now, what do I multiply 3 by to get to this 42? So to figure that out, I'll just divide by 3. So it's by 14. Before I thought something was wrong because I ended up with this negative 154, which nothing evenly went into it, which made me think, okay, maybe there's a mistake. and there was. But now that it's 42, I'm going to multiply this thing by 14. Anyway, so we have 14 there. It gives us 42x, that's much better. But then 14 times 7, we get negative 98. Now, when I take the difference, that's negative 106 plus 98, so my remainder is negative 8. What does all this mean? Well, I guess we talked about before. If you took 3x minus 7 and multiplied it to 3x cubed plus 3x squared minus 8x plus 14, that is almost equal to the original polynomial of 9x to the fourth minus 12x cubed minus 45x squared plus 98x minus 106. The only difference is you have to subtract 8 to make these two things equal to each other. So for these problems, 23 through 28, I want to try to do as much as possible from the graph, where the goal is to factor this. If you can guess every single factor, you can write down the final answer very quickly. So I went to my graphing calculator, and when I entered this equation, I was just looking for the places where it was crossing over the x-axis. And I saw negative 5 and 1 both gave me 0. There was a third one that's, it's between two numbers. I wasn't quite sure what that is. But at the very least, I knew my answer would have to be y is equal to x plus 5 times x minus 1, but then times something else. What is that other thing? It's got to be, something times x plus or minus a number. You can use long division like we did in class, but at this point, I think we can pretty much guess the answer. The product of these three terms has to take me to a 2x cubed. This is definitely a 1x. That is a 1x. For this whole thing to work out, there would have to be a 2 here. So I'm just going to go ahead and put in, well, that's got to be 2. Now, the numbers at the very end that go here, here, and eventually what we'll put here, that has to multiply to negative 5. 5 times negative 1 is negative 5 times a positive 1 would make this entire equation true. So we could use long division, but it must be that It must be that the very last factor is 2x plus 1. Now, what does that mean in terms of our table? What other number makes this graph equal to 0? And the answer is x is equal to negative 1/2. That is the number that when you put it in place of x makes this thing 0. So negative 1/2, you could even check this in your table, it should give you 0 over here. But really, once you get to this part of the answer, we're done. It might be nice to write this down so you can at least compare it to the graph to see that it makes sense. So for 24, again, I graphed this polynomial, and my goal was to guess as many of the zeros as possible. And by looking at the graph, there's definitely 3. One's between 0 and 1. I'm not quite sure what that is yet, but definitely 2 and 7 gave me 0 back, meaning if I'm going to start this problem, it's going to be x minus 2 times x minus 7, and then some other mystery factor that I just don't know. But again, we could use division to figure it out, or perhaps we could just guess by thinking about numbers that multiply back to 3x cubed and then a negative 28. So x times, well, it would have to be a 3x to get a 3x cubed. And the last thing is deciding, okay, if I want negative 28, negative 2 times negative 7 is positive 14. Okay, so I know it has to be a minus something. And if I double 14, I get to 28. That's the last factor. It's got to be 3x minus 2. Now the question is, if I wanted to check this in my graphing calculator, what number makes this factor 0? Well, it has to be positive because I have a negative here. 2 will be in the numerator and 3 will be in the denominator. It's going to be positive 2/3. And you can even check this in your graphing calculator. I'm going to give that a shot here. Okay, I typed in 2/3. It gave me a decimal back for x, but for y, it told me that 0 is the answer. question 25. I graphed this and there are definitely 3 zeros, but I guess only one I know for sure. It looks like it's at -3, so I'm just going to type that in, and it is. It went to my table. I typed in -3, and I got 0 back. So if I'm looking to factor this equation, there's for sure 3 separate factors, but one of them has to be x plus 3. Well, we could try guessing like what the other 2 factors would be. If you could guess the numbers that make it 0, this process would be pretty simple, but I think I'm going to actually use long division to figure this out. And by that I mean I'm going to take that factor of x plus 3 and I'm going to divide it into 6x cubed plus 31x squared plus 44x plus 15. It has to give me a remainder of 0, and the thing that's left over I should be able to factor, hopefully. So let's see. All right, I'm going to multiply by 6x squared because I get 6x cubed, but then plus 18x squared. I am taking the difference of these two things. All right, so we get 13 x squared plus 44x. That means I'd have to multiply by 13x. I get 13x squared, and I get 39x. If I take the difference, the x squareds cancel, and I get 5x, and I'll bring down the 15. This is going to work out because I'm now going to multiply by 5. It gives me 5x plus 15. That is perfect. I knew I had to have a remainder of 0. So whatever the 2 factors are here, they have to multiply to this thing, 6x squared plus 13x plus 5. I'm going to just try to guess the factors of this thing. 6x squared plus 13x plus 5. How would this thing break apart? There's a couple of ways that this could happen, but maybe it's like a 2x and a 3x. Everything's got to be positive. And then I guess I'd have to have a 1 and a 5 or a 5 and a 1. I just want to make sure I put those 2 numbers in the appropriate place, so it multiplies to give me a 13x. If I put 5 here, I get 10. If I put a 1 here, I get 3, and 10 and 3 is 13. Okay, so that's plus 1 and plus 5. Those are my other 2 factors. And if you check this out, x times 2x times 3x is definitely 6x cubed. 3 times 1 times 5 is a positive 15. If I want to be extra careful, use my graphing calculator to check my work. This factor is equal to 0. It's got to be at -1 divided by 2. And this other one is also negative 5 over 3. Again, where this is coming from, this makes the numerator and this makes the denominator. I'm going to type these both into my calculator and hopefully I'll get 0 back for both of these values. Let's see. -1/2 tells me 0. Perfect. -5/3 also says 0. Okay, I'm convinced that I factored this thing correctly. So again, here we have a polynomial where it looks like one of the zeros is -2, and I'm not 100% certain on the others. You could try guessing them if you want, but I do know -2 definitely is a 0. Okay, that's good. So whatever this means about this polynomial, it has to have x plus 2 as a factor, and potentially 2 others. Okay, I'm going to use polynomial division again, where I'll take x plus 2 and divide that into 9x cubed plus 27x squared plus 14x minus 8. So I'll multiply by 9x squared. That gives me 9x cubed plus 18x squared. And when I take the difference of those two things, I get 9x squared plus 14x. So now we'll multiply by 9x to give me 9x squared plus 18x. When I take the difference, I get negative 4x minus 8. All right, so I'm now going to multiply by negative 4. Okay, that works out perfect. I get negative 4x minus 8. Clearly, if I take the difference of those two things, you get a remainder of 0. So we have that 9x squared plus 9x minus 4 can be factored into two pieces. And I know, if I'm going to guess this, your choices are to put a 3 and a 3 or a 9 and a 1. 9 and a 1 is impossible. We already know that 1 plus or minus something would be an integer answer, which didn't happen. So I'm going to use a 3x and a 3x. You have to have a positive and a negative if you want to multiply to 4. So it's got to be either positive 1, negative 4, or positive 4, negative 1. Since the middle term is positive, I'm going to go positive 4, negative 1. And that works. That's going to be a 12x minus a 3x to give us a 9x. Nice. So this is 3x plus 4 and then 3x minus 1. Just to double check this, x times 3x is a 9x cubed. 2 times 4 is 8 times negative 1 is negative 8. This is looking great so far. Looking down here, my other two zeros are negative 4 thirds, and this one would have to be a positive 1/3. I'm just going to check that in my table. Does 1/3 give me a 0? Does negative 4 thirds give me another? So I typed in 1/3. Yep, okay, that's good. Negative 4 thirds, also good. Okay, so I've factored this polynomial. From the graph, I see that negative 6 is a 0. I just don't know the other two. So that has to be x plus 6, and then there are two distinct other zeros. All right, so I have to have two other factors. You know, I wonder if we can guess without even doing division by using this 8 and this 18. So here's what I mean by that. You don't have to take this approach, but I do know that anything that multiplies to give me an 8 would have to be something like a 1 times a 2 times a 4, or a 1 times a 1 times an 8. So I'm thinking one of these has to be 2, and the other has to be 4. So I'm going to go ahead and write that in. If this is going to work out, it's got to be 2, it's got to be 4. You couldn't have a 1 for one of these because that means we'd have an integer answer. Okay, lastly, all right, I want to multiply to a negative 18. Well, 6 times something gives me 18. 6 times 3 is 18. That means one of these is a 3, the other is a 1, one's positive and one is negative. I'm going to just try a couple of cases to see what happens. So at this point, I'm just going to make some guesses. Here's a possibility. It could be that this is a negative 1, and therefore this would have to be a positive 3. That could be wrong, but I can use my table to see if it's true or not. So I know clearly negative 6 works. But here, it would have to be negative 3 halves and positive 1/4 that make the table equal 0. I'm going to check those. So negative 3 halves. Ooh, when I type in negative 3 halves, it gave me 135. Didn't work. What about 1/4? Also didn't work. When I typed in 1/4, it gave me negative 31.25. Also no good. So all this means is that my guesses were incorrect. Well, another possibility would be, well, maybe it's negative 3 and positive 1. I'm going to make that guess. So, we tried this out. Those just were no good. So I'm going to go back to the drawing board and say, okay, well, what about 2x minus 3 and 4x plus 1? in my table, again, we know that x equals negative 6 works, but then it would have to be positive 3 halves and negative 1/4. Let's see. Negative 1/4. Okay, negative 1/4 gave me 0. This is perfect. Okay, so if I look at my table, again, negative 6 gave me 0, but negative 1/4 gave me 0 as well. If I check positive 3 halves, that also gave me 0. Nice. What this means is without even using polynomial division, just what the zeros are of this equation, I was able to factor it. And for this last one, I guess I put this one on here just because it's difficult. When I graph the equation, I don't see any integer zeros. So that's a problem in terms of coming up with something to divide by, or at least writing down what the factors are equal to. But when I look at my graph, I'm going to make an effort to guess what the zeros are. There is a 0. It's between negative 2 and negative 3. I mean, there's something, around here. Okay, there's also something between 0 and 1, maybe around here. And then there's something between 3 and 4. Maybe halfway between, I can't really tell. If I could guess the fractions, it means I could write down the factors. This thing definitely factors into 3 pieces. I just need to guess what the fractions are for those 3 zeros. All right. There's a trick I'm going to use here where I'm going to write down the factors of 35 and 12. I'll start with 35. The factors are 1, 5, 7, and 35. The factors of 12 are 1, 2, 3, 4, 6, and 12. When it comes to guessing the numbers that go in front of the x's and the numbers that go at the end by themselves, any number that you put here has to multiply to 35. It means you should only be guessing 1, 5, 7, 35, possibly plus or minus. And the numbers that you put in front of the x's, you should only guess 1, 2, 3, 4, 6, and 12. Like, there's no way it could be 5. That would never multiply to give you 12. I think this will make guessing the zeros a little bit easier. Let's focus on this one first. The answer is between 0 and 1. So some possibilities would be like 1 divided by 2, or maybe 1 divided by 3, or 1 divided by 4. I'm going to go into my table and just plug those in to see what happens. I'm going to make some guesses. Okay, I typed in a half, and it told me negative 18, so nope. Okay, no good. Maybe I could try a third. Okay, that one worked. And all right, that must mean that one of my factors is 3x minus 1. Okay. So that took care of this 0. I now need one for this spot and this spot. It's gotta be that they both start with a 2. So I'm gonna go ahead and label that in there, put a 2 here and a 2 here. For this to work out, actually, I already know what the answer is. I need 2 numbers that are going to multiply to a positive 35, and then I have a negative here. So it's got to be that one is positive and one is negative. The one that's negative corresponds to this 0 here. The one that's positive corresponds to this 0 here. I'm thinking that it's going to be positive 5 and negative 7, because the zeros will be negative 5 halves and positive 7 halves. I'm going to check those in my table. Okay, negative 5 halves and 7 halves. They both work. All right, so you could again try to use some division, but this was a pretty challenging problem because I graphed the equation and I couldn't instantly tell what those zeros were. But with a little bit of guesswork, I was able to get, well, this one, this 3x minus 1. That then got the ball rolling on the other two zeros. So this is the factorization for this polynomial, and that is it.